Okay, page 5, side 2 is going to look at acid strength. So the stronger the acid, the weaker its conjugate base is going to be. So this is analyzing the pairs. So the stronger the base is, the weaker its conjugate acid is. So they're always opposite. So we want to identify conjugate acid pairs. So if you see we have HNO3 with NO3, that's one pair. And we want to identify them. You should recognize HNO3 as a strong acid. So this is a strong acid. And I'm going to use just SA, since the writing on this is not going so great. So that's a strong acid. So that means that this would be a weak base. And then if we're looking at this pair, H2O and 8-hydronium is a pair. So since this is an acid, this would have to be a weak base. So water's amphoteric, so remember, can be either. And that would make hydronium and acid. Now, I'm not really going to label this one strong or weak. A lot of people will say this was a strong acid. It's obviously stronger than most acids, but I would label it as strong as the hydronium produced from HNO3. So we look at reactivity based on proceeding to a greater extent with a strong acid and strong base forming a weaker acid and a weaker base. So we're going to be looking at this equation for A. You smell ammonia when NH3 dissolves in water. So we're going to write the equation. So NH3 is ammonia plus water is in equilibrium forming NH4 plus, that's the ammonium ion, plus OH minus. So again, NH3 is a weak base. Okay, this is going to make water a weak acid. Okay, NH4 is going to be a weak acid. So again, it doesn't fit the definition of a strong acid, and hydroxide in its pure form would be a strong base. So, because you have a stronger base here, the reaction proceeds to the right. Okay, it's reactive driven. And I apologize, I don't know why this device is not working very well, so you just have to listen carefully. Remember, you can stop it right away if you need to. And again, that's evidenced by what we observe. So you smell the NO3, that means that the equilibrium is further to the right. When we go to part B, we see that the odor goes away. So the fact that the odor goes away tells us that the reaction is going to proceed to the product side. And the question is why when we're adding an excess of hydrochloric acid. So this is going to be a strong acid. It's going to react with the hydroxide. So the strongest acid is going to react with the strongest base to form water. And what this is doing is removing hydroxide. So this comes back to Le Chalier's principle. If we remove a product, that's going to shift our equilibrium. So the equation's going to try, the system's going to try to adjust by creating more product. So that's why it shifts to the product side or to the left to try to make up for this hydroxide that's being lost. Key thing here, we have some excesses, so excess hydrochloric acid and excess sodium hydroxide. So when we start taking hydroxide, or start adding more hydroxide, again, it's going to react with some of the excess hydrogen. So you have excesses in both of this, so you're going to see more water formation initially, and then once there's an excess of hydroxide, so with excess OH, You're going to shift your equilibrium back to the other side because now we have an excess of hydroxide, and it's again Le Chatelier's principle that it's going to adjust by shifting back to the the reactant side, and you're going to get that ammonia smell back because more ammonia is being formed again. So again, all of these are looking at acid-base chemistry and Le Chatelier's principle. Okay, for the dissociation of HF into H plus and F minus, it's a weak acid. Again, there's a negative small exponent up for the Ka. We're going to set up an ice table, so just like any other equilibrium. So you're going to see that this is very similar to what we had before. Initially, you have none of the product, and after equilibrium, you are going to add each of the products and subtract the reactants. Excuse me. And you're just going to set this up into your Ka expression. So just like any other equilibrium, its products over reactants, so that's your basic equation, and then you're just substituting your values in. So this x value here is very small since we have a 10 to the negative 4th exponent. Okay, this is 10 to the minus 1, so there's 3 powers there, so we can drop that and just solve for x squared. So 1.75 times 10 to the minus 4th comes from doing 3.5 times 0.5 equals x squared. And then x is going to be the square root of that, which is 1.3 times 10 to the negative 2nd. Now, that is equal to your H plus concentration, or your hydronium. So you're going to get the pH, you're going to do the negative log of that. That should be 1.3. So 1.3 times 10 to the negative 2nd is going to give you a pH of 1.88.